Hello students, and welcome to our lesson on useful properties. What we're going to be doing in this lesson is laying the groundwork for equation solving that's going to be coming afterward. So we're going to learn about identities, inverses, the commutative and associative properties. We're going to talk a little bit about variables and combining like terms. And most importantly, we're going to learn about properties of zero and the distributive property. So a whole bunch of useful properties that are going to help us solve equations in the following lessons. A lot of these you have probably used without actually realizing you were using them. So we're going to formalize it by putting the name to the operation now. So starting off nice and easy with identity properties. An identity is essentially something that does nothing, right? So for addition and multiplication, we will have an identity for each. We're going to start with addition. So when we are talking about things related to addition, we refer to it, the property, as being an additive property. So additive, just like addition, but additive. And the additive identity is going to be zero because adding zero to any number does not change its value. So the idea here of an identity is to accomplish nothing. So you can see down there, a plus zero equals a, and zero plus a equals a. No matter which side you put that zero on, it's not going to do anything. We're going to go from a to a in both cases, and that zero is not going to change anything. So for example, we could have 7 plus 0 equals 7, or 0 plus 7 equals 7. Either way we put that 0 on there, we're going to end up with the same number we started with. Now for multiplication, whenever we talk about properties involving multiplication, we refer to it as a multiplicative property. So multiplicative, forgot the C there. Nice big word for us. So the multiplicative identity is going to be 1 because multiplying 1 does not change the number's value. So if we do a times 1 or 1 times a, we're still just going to end up with a, the thing we started with. So now the reason we introduce those identities first is because now when we talk about inverses, it has to do with those identities. So we need to know that the additive identity is 0 and the multiplicative identity is 1. All right, so now inverses. An inverse, quote unquote, undoes a number by creating the corresponding identity. So an inverse operation is just anything that undoes the original thing. So it's like the reverse, right? If you put your car in drive and go forward, the inverse of that would be going in reverse, going back to where you started. The additive inverse of a number is its opposite. So if you recall from previous lessons, we talked about opposites of numbers. That just means to make the number negative, or if it already is negative, make it positive. And together, a number and its opposite make the additive identity, which is 0. So for example, if we have a plus negative a, that gives us 0 because the a's cancel each other. Or 7 plus negative 7 is going to give us 0 because we just take away the 7 we added. Notice here, we are getting the identity as our result. So the idea of the inverse of a number is to get back to the identity. So very closely tied together, these words identity and inverse. Okay, the multiplicative inverse of a number is going to be its reciprocal. So now we've already talked about fractions, so we know that a reciprocal means to flip the fraction upside down. And together, a number and its multiplicative identity, or together a number and its multiplicative inverse, I should say, will make the multiplicative identity, which is 1. So any number times its reciprocal, so if we start with a and we multiply by 1 over a, that is going to get us back to 1, which is the multiplicative identity. And this works as long as a is not 0. 0 does not have a multiplicative inverse because there's nothing you can multiply 0 by to get to 1. So this works for anything except 0. So as an example, we use our favorite number 7. 7 multiplied by its reciprocal, 1 over 7, is equal to 1, where that 7 on top cancels that 7 on bottom. And we have seen work with fractions where we should be able to recognize that multiplying by the reciprocal right here is the same as just dividing by the original number. So we could be saying that 7 divided by 7 gives us 1, but multiplying by the reciprocal like this is the same thing. And this is going to work better in some cases. Whenever we deal with fractions, thinking of it as multiplied by the reciprocal is going to be easier than thinking of it as division. But technically, all we are doing for this multiplicative inverse is dividing. But because it's a multiplicative inverse, we can't really say division, right? So we're going to call it multiplicative inverse, and that is the reciprocal. So a couple examples down here. We've already used our number 7 a couple times, so we've seen this first row. But what we're going to be doing is filling in what the additive and multiplicative inverse is, and then just writing the proof, where we write that number in to show that it does in fact equal the identity in each case. So for 7, the additive inverse is its opposite, negative 7. 7 plus negative 7 gives us 0, which is the additive identity. The multiplicative inverse of 7 is 1 over 7, and 7 times 1 over 7, the 7 on top cancels the 7 on bottom, so that just gives us 1. Now, the reason I have this whole table here is so we can see how this works for different types of numbers. So a normal positive integer is the easiest to see this for, right? 7, the opposite just becomes negative 7. The multiplicative inverse just becomes 1 over 7. That's as simple as it gets. But we can do this with any type of number. So let's do a negative now. The additive inverse of negative 12 is going to be positive 12, because if we add negative and positive 12, we get 0. And the multiplicative inverse, we have to keep that negative sign. So it's going to be negative 1 over 12. When you do the reciprocal, that negative sign doesn't go anywhere. So now the proof is that negative 12 times negative 1 over 12. Notice the negative signs cancel and the 12s cancel, so we just get that identity, which is 1. For fractions, 3/5, if we flip it, or if we want to do the additive inverse, we make it negative 3/5. So additive inverse is always easy, just change the sign. For the multiplicative inverse, though, we have to flip it over, so we're going to get 5 over 3. 3 over 5 times 5 over 3, the 5s will cancel, the 3s will cancel, and we just get 1. If that fraction is negative, like negative 7 over 9, we're just going to change it to a positive, so positive 9 over 7. We actually don't need that addition symbol. So negative 7, oh, whoa, big mistake there. Let's get rid of that one. We needed positive 7 over 9, not the reciprocal. And let me point out that this is the mistake students make as well, not just your professor, Mr. K here. So when we're doing additive and multiplicative inverses, just always got to keep it straight. Additive purely means change the sign. Multiplicative inverse means flip it over, but do not change the sign. So for the additive inverse of negative 7 over 9, positive 7 over 9, because those will add together to give us 0. But for the multiplicative inverse, we keep it negative and we flip it over. So negative 9 over 7. And when we multiply negative 7 over 9 times negative 9 over 7, the 9s, the 7s, and the negative signs cancel, so we just get 1. With decimals, you could turn it into a fraction and then apply the properties with fractions like we just did, or you can actually just leave it as a decimal. So 4.8, the additive inverse will just be negative 4.8. Those will add to give us 0. And for the multiplicative inverse, you just have to write it as 1 over that number, the same way we did for the integers at the top. So the multiplicative inverse of 4.8 is 1 over 4.8, where all we do is put that number on bottom. So 1 over 4.8 multiplied by 4.8 will just give us 1. For negative 0.25, we're going to make it positive for the additive inverse. Those will add to give us 0. And for the multiplicative inverse, the reciprocal, we keep the negative sign and we put that 0.25 down in the denominator. So we just flip that upside down. So 0.25 as negative times negative 1 over 0.25. The negatives will cancel and the 0.25s will cancel to just give us 1. So that is our first couple properties, identities and inverses. Now we're going to talk a little bit about variables. And I know in this class that we have used variables already because we have combined or we've substituted in for variables in previous problems, such as in the order of operations lesson. But we're going to formalize what variables are doing for us. And we're going to talk about combining like terms, which is when we are allowed to combine and not combine variables. So up there at the top, a variable is a letter that represents an unknown or a changeable number. So it doesn't necessarily have to be unknown. It could just be a number that we want to be able to change later. But generally speaking, a variable for us will represent a value we do not know yet, called an unknown. So x plus 5 equals 12 would read as some number plus 5 equals 12, where this phrase here, some number, is that x variable. So it's just a number that we don't know yet, but that we can solve for in the future. And variables are going to let us write expressions using values that we don't know yet. So I do not know what that x is in the previous line, but I'm still able to write an expression without knowing what number goes in that place. And it allows me to then fill in that number in the future, or depending on our situation, we might be solving for that number using some sort of equation solving steps, which will be the next couple lessons. So now, why do we care about variables and how do we work with them? Well, we have these things called terms in an expression, and terms are separated by addition and subtraction. This is key here, where wherever you see a plus or a minus sign in the problem, that is going to separate terms. All right. And the terms can be a few different things. They can be constants, which are just numbers. Okay. So whenever you hear the word constant, just think number. Or they could be variables, which are the letters, like we just saw a second ago. So variables are letters. Or they can be the product of constants and variables. So they are either just numbers, just letters, or the product of numbers and letters. So for example, we could have the number 5, that's a term, and it is a constant. Or we could have the letter x, that is a term, and that is a variable. Or we could have those multiplied together as 5x, where that is the product of constants and variables. So it's either just a number, just a letter, or the product, so multiplied together, letters and numbers. Now, like terms, that is a phrase used to describe terms that we can put together. Okay, like terms have the same variable raised to the same power. And we're not going to work with powers too much in this course, but powers refer to exponents, which we've seen a little bit of. And the variable being the same literally means it has to be the same letters that are in the term. So down below in the next line, to combine like terms, we will add or subtract what are called coefficients. And these are the numbers or the constants in front of the variable. So for example, the coefficient of 5x over here is just the number 5. Okay, it's just that number that's attached to the variable. So to combine like terms, we will add or subtract the coefficients. So for example, we could do 3x plus 7x equals 10x, where we add together, because there's an addition symbol in the middle, we add together the 3 and the 7 to get 10, and the variable stays the same. We don't change the variable. And if you're wondering, Mr. K, how does this make any sense? Well, let's think about some cars for a second. If you have 3 cars and I have 7 cars, together we have 10 cars. Notice we added the 3 and the 7, but the word cars did not change. So then if I wanted to calculate how much money in cars we have, I could just replace the letter X or the word cars in my sentence with whatever number the cars are worth. So for example, if you have 3 cars that are worth $10,000 each, and I have 7 cars that are $10,000 each, together we have 10 cars that are $10,000 each. So we multiply 10 times 10,000 and we have $100,000 in cars. But notice that when I put them together, I didn't change the number 10,000. Yours are worth 10,000, mine are worth 10,000. So together we have a bunch of cars that are worth 10,000. That part of it does not change. The variable stays the variable, but we add together the coefficients because that is us counting how many of that variable we have. So 3x plus 7x, we just add 3 and 7 to get 10x. But in the next one, 3x plus 7y, these cannot be combined because the variables are different. So an x and y are not allowed to be put together. Okay, if you have 3 cars and I have 7 boats, we do not have 10 cars and boats, or well, we do have 10 cars and boats, but we don't put together the boats and the cars as one thing. So if you have 3 cars and I have 7 boats, you wouldn't say that we have 10 cars, right? You wouldn't turn my boats into cars as a way to put them together. We have 10 vehicles, sure, but that's a whole new variable, right? If you have 3 cars, I have 7 boats, we leave those things separate. We're not going to put those together to count them. So different variables stay separate. All right, let's do a couple examples down here. We have number one, 4x plus 7x minus 3. We can put together the 4x and the 7x to get 11x, but that minus 3 is not a like term, so it stays separate. So just 11x minus 3. And it's not a like term because it does not have an x like the other two do. In the next one, we have 6a plus 2a minus 5 plus 9 minus 2. The only things with a's are the 6a and 2a, so we add those coefficients to get 8a. And then all the constants here, we just add and subtract like normal. Negative 5 plus 9 minus 2 is going to add up to be positive 2. So altogether, we have 8a plus 2. Last one, number 3, we have 3m plus 2m minus 5n. Notice the letter changed, okay, different variable for the 5n. So we're going to combine like terms. 3m plus 2m is 5m, but that negative 5n is going to stay separate because it has a different variable. All right, so now notice in all of those, I had the x's next to the x's and the constants separate in the first one. In the second one, I had the a's next to the a's and all the constants separate to the right. And same thing in number 3, I had the m's next to the m's. Well, that's not always going to be the case. A lot of the time, we're going to be given expressions where the variables and constants are all over the place. So we still need to be able to combine like terms without them being already next to each other. So we have two properties here, the commutative property and the associative property. And these are the ones that I mentioned you might already know, but just didn't know the names for and didn't know you were using them. But these are what are going to allow us to put together like terms and simplify expressions when everything's jumbled up and messed around. So what they allow us to do, the commutative property allows us to change the order of addition or multiplication. So the order of addition and multiplication does not affect the result. If we do a plus b, that's the same as doing b plus a. And similarly, a times b is the same as b times a. Okay? The associative property, though, is going to allow us to change the grouping of things that are happening. So for example, if we wanted to add together three numbers, a, b, and c, I can add them in whatever order I want. I can do a plus b first, which is what those parentheses tell me, and then add c, or I could add b plus c first, and then add a. So the associative property allows us to change the place of these parentheses and put it around different parts of the expression. And this works whenever we have all addition or we have all multiplication. So for multiplication, same deal. We could do a times b and then multiply by c, or we could do b times c and then multiply by a. And even though we did it in a different grouping, we're going to get the same result because this does not affect the value of that result. So let's go ahead and see it. For these 4, 5, and 6, I'm going to be very explicit and write out these properties. But just know that normally we don't describe that we're using these. We just go ahead and use them automatically. So let me real quick give you an example of what using it automatically would look like. Number 4, we have 5x plus 10 plus 3x plus 4. I would combine 5x and 3x to get 8x, combine 10 and 4 to get 14, and I would be done. That's really all there is to it. But we have these properties, and I want to show you how to use them because I just used them without it even being shown at all. I kind of skipped straight to it. So let's see it written out. All right, first thing we're going to do is change the order of what's going on here. So we are going to use the commutative property to rewrite this as instead of 5x plus 10 plus 3x plus 4, we're going to switch the places of the 10 and the 3x. So we're going to rewrite it as 5x plus 3x plus 10 plus 4, where all I did was change the order there. Now, instead of right now where there's no parentheses around it, what I'm going to do is use the associative property to specify the grouping that I'm going to multiply these in, or sorry, that I'm going to add these in. So specifically, I'm going to put parentheses around 5x plus 3x to make it clear that I'm going to add together the x terms, and that's going to give me 8x. And then I'm going to put parentheses around the 10 and the 4 to make it clear that I'm going to add together the 10 and the 4 to get 14. And so I got the same answer that I showed you at the beginning, 8x plus 14, but it's those properties in the middle that make it so I'm allowed to do that. In general, you can't just change the order of everything willy-nilly. But when you have all addition like this, or if you had all multiplication, you're allowed to change the order and you're allowed to regroup to add or multiply things in different orders. All right, number 5, we have 2x plus 7 in parentheses and then plus 3. So in this case, we only have to use one property. We're just going to use the associative property, which I'm going to write here. That is going to allow me to regroup. So instead of doing 2x plus 7 in parentheses, I'm going to do 2x plus, and then 7 plus 3 is going to be my new grouping. So I'll leave the 2x alone, add the 7 and the 3. This is 2x plus 10. And that's it. We're done with that one. Okay, number 6, we have 5 times 2 multiplied by x times 7. What I'm going to do is use the commutative property first to switch the places of the x and the 7. So I'm going to leave it as 5 times 2 in front, multiplied by, but I'm just going to switch the x and the 7 to make it 7 times x. Then I'm going to use the associative property to make it so that I have all the constants multiplied together and the variable left out. So 5 times 2 times 7, all in parentheses, and then multiplied by x. And now this allows me to just multiply the numbers all together. So 5 times 2 times 7 gives me 70, and I just have that x all alone. So again, these properties are not going to be something we write out like this step by step in general, but we need to know that we're allowed to do these things. And why are we allowed to do them? Well, it's because we have these properties that are well established for both addition and multiplication. Notice that they are not established for subtraction or division because those will break when you switch the order of events. But for addition and multiplication, all good across the board here. All right, now our most important property, and that is the distributive property. So multiplication distributes over addition and subtraction. And what that means is if we have an A multiplied by a B plus C, this is the same thing as multiplying A times B and then A times C and adding them together. So notice I drew those lines over top. Let me do it again for you here. A times B, that's AB, and then A times C, that's AC, and we keep that addition symbol in the middle. So we just drop down that addition symbol. So we can distribute the A that's in front of the parentheses to everything inside. And it works just as well with negatives. So if we distribute A to B minus C, we will just get AB minus AC, where again, the A multiplies by each thing inside. We distribute the A. So for number 7, we have 5 parentheses x plus 7. We're going to distribute this 5 to the x and the 7. 5 times x is 5x, and 5 times 7 is 35. That's the most basic case where we don't have to deal with any negatives, but of course we can kick that up a notch. Number 8, we have negative 2 in front of 3y minus 4. So we're going to distribute this whole thing, negative 2, to both objects inside. Negative 2 times 3y is negative 6y, where we multiply the negative 2 and the 3, and the y stays alone. And if you're wondering, hey, why are we allowed to just multiply the negative 2 and the 3? Why doesn't the y change? Well, think about the commutative and associative properties again. I have negative 2 times 3 times y, so I can do the negative 2 times 3 to get negative 6, and then just times y, which really just means to leave that y attached to the backside. Okay, finishing this one off, negative 2 distributes to the negative 4 also. A negative 2 times a negative 4 will give me a positive 8. And notice that I need to write this addition symbol here, because when I distribute this negative, I get plus 8. But if I don't write the addition symbol, if I just write the number positive 8 right there, then I'm not going to know what operation is in between. So this tells me that the negative or the subtraction here became addition. All right, number 9, we're going to have 2 of these. We have a negative sign in front of an x minus 5. That really means negative 1 in front of x minus 5. So if we don't write that 1 there, if we just put the negative sign, it means that there is a 1. And then we're going to be subtracting 3 times y plus 4. So we're going to distribute the negative 1 to the x minus 5. Negative 1 times x is negative x. Negative 1 times negative 5 is going to be positive 5. And then when we distribute the negative 3 to the y plus 4, negative 3 times y is just negative 3y. And negative 3 times 4 is going to give us negative 12. Then we can combine like terms. Using the associative and commutative properties, I can move that 5 to the back. So it's going to be negative x minus 3y, and then positive 5 minus 12 is negative 7 on the backside there. And I'm going to add some equal signs here just to make it look cleaner if you guys look back at these notes. All right, so that last one, negative x minus 3y minus 7. All right, now I got a fun little problem for us that involves the distributive property. And I actually use this in my everyday life, but only in special circumstances. And that special circumstance is when a price ends with 99 cents. Okay, so here, Adelaide is a former student of mine. She told me that she was buying shampoo for $3.99 per bottle at the grocery store. So I asked her what shampoo, and I found out that I could get that same shampoo as a 3-pack for $9.99 at a bulk store. So the question now is, how much would Adelaide save per 3 bottles if she purchases the 3-pack? And we're going to solve this using the fact that $3.99 is equivalent to 4 minus 0.01. So if you have $4 and you take away 1 penny, that gives you $3.99. So those are the same thing. All right, so now how are we going to do this? We know that the 3-pack is $9.99, and we want to find out the savings per 3 bottles. So what we need to find out is how much just 3 bottles cost at $3.99 per bottle. So we're going to do $3.99 multiplied by 3. But look at that multiplication I just wrote. 3.99 times 3. That's not fun to write. I don't want to do that, so I'm not going to. Okay, instead, I'm going to do 3 multiplied by 4 minus 0.01. We're notice right here that this 4 minus 0.01 is $3.99. So I'm multiplying 3 by $3.99, but I'm doing it in a strange way. Okay, so now why? How is this easier than just multiplying 3 times $3.99? Well, watch what happens when I use the distributive property here. 3 times 4 is going to give me 12, and 3 times 0.01 is 0.03. So what's $12 minus 3 cents? That is $11.97. I promise you that I can do that faster than I can do 3 times 3.99. Okay, so if I round up to 4, multiply 3 times 4 to get 12, then I just have to subtract the part that I should be removing. And that's that 3 cents right here. So we can use the distributive property to make multiplication by these weird prices a little bit easier on us. All right, so now the actual question is, how much is she saving per 3 bottles? So she was paying a rate of $11.99 per 3 bottles. And at the bulk store, it's $9.99. So if we just subtract these two prices, we'll get what the savings is. And this subtraction works out to, let's see, an 8 there, a 9 here, a 1 there, $1.98. Okay, so it is a $1.98 savings by purchasing in bulk. And so now I'm not saying that's a massive savings. So depending on how much shampoo you go through, that might be only $5 a year. But hey, saving money is saving money, guys. All right, last thing we're going to talk about, properties of zero. This is arguably the easiest part of this because they're just facts. They're not something we have to like go through and do deep equations for or anything. Just some facts here. And all we're really showing is that when you multiply by 0, you get 0. And when you divide by 0, we don't know what you get, okay? So for any real number other than 0, we have this fact that 0 over x equals 0. Okay, so if you have 0 divided by anything, that is 0. Because if you try to take 0 things and split it into some number of groups, there's going to be 0 things in each group. Okay, as long as the number of groups is not 0. Division by 0 is called undefined because we actually don't really have a way to explain what it is. It breaks our logic for division. So if you do x divided by 0 in any context, that answer does not exist. And if you try to do it on a calculator, it will tell you error. Okay, it is not defined, even for the calculator. All right, and then multiplication by 0 always gives us 0. So just like the first bullet point, no matter what we multiply by, if 0 is the thing that we're multiplying with, we're always going to get 0 at the end. So quick examples here. If we have 0 over 36, like number 11, that is just 0, because you're taking 0 objects, splitting into 36 groups. There is 0 in each group. Number 12, 0 times 1/2 is 0, because we're multiplying by 0. Number 13, 2 over 0 is undefined because we cannot divide by 0. And number 14, 17 over 5 divided by 0 is still undefined. So I wrote it in a funny format to try to trick you, but when you have that division by 0, it is always undefined no matter how you write it down. So if at any point in your problems you are dividing by 0, undefined is what we call that. All right, thank you for joining me for this lesson on useful properties, and I'll see you next time for solving equations.